Today, I'm going to present you a project that I built from the ground up, DemandIQ NL. It is a predictive supply chain intelligence system end-to-end, from raw data ingestion to machine learning to a Power BI live dashboard. And it was built to solve a problem that was costing this business a real money every single day. My name is Patel and I'm a data analyst at Patel Mart, a fictional Dutch FMCG distributor that has headquartered in Utrecht. The name itself clearly, demand IQ, making inventory decision intelligence and not intuitive. Let me start by telling you about the company. Now let's talk about Patel Mart. Patel Mart is a regional and fictional FMCG distributor based in Utrecht. We supply 10 stores across Netherlands, carrying over 3,000 active SKUs within 27.3 million annual revenue. Now, folks who doesn't have any idea about what is SKUs, that is stock keeping unit, is a unique alpha numerical code used by retailers to internally track inventory, identify the product variation, and manage stock level. So if we have come across any nearest Albertine or any supermarket and we see there is a certain product selling the discount and then we try to match the code, which is specifically mentioned that this code is in the discount and we try to match the product having that particular code. So that code is itself called SKUs. So as a company, we sit between manufacturer and the retailer. That means every inefficiency in our inventory decision has a direct impact. Too little stock and the shelf is empty, too much stock, and our working capital is locked in the warehouse. The challenge at the scale is real. 3,000 SKUs across 10 locations is 30,000 possible SKU store combination to monitor. No demand planner can do that manually. We neither had any system that could address that. So in this project, that gap, DemandIQ NL, was built to fill. Now, folks, here is the honest picture of where Patel Mart was before DemandIQ NL. Two costly problems running in the parallel every single day. Imagine it's a Friday. You walk into Albertine after your work to grab some ingredients for the dinner. Maybe chicken, maybe that specific pasta sauce that your friends and family likes. And the shelf is empty. You're frustrated. And you grab something else, or in worst case, you go to Yumbo instead. One side, the stock out, a SKU running out from the stock. So the shelf is empty, the customer does not wait. They go to a competitor and revenue is lost permanently. On high velocity voiding products, this was recurring problem. On the other side, overstock, too much inventory sitting in the warehouse, working capital tied up, product approaching expiry getting discounted or written off entirely. That is margin lost and not because of the market, but because of how we were managing the stock. Both problems share one root cause. We had no reliable system to know which SKUs in which store were about to fail before they failed. So Demand IQ NL was built to make this anticipate or forecast this problem. Now, before we build anything, we need to understand the size of the problem. What was the flat 14 days rule actually costing us? We modeled the difference between the manual approach, 14 days of stock or uniform across all SKUs, and statistically calibrated safety stock, calculated per SKU based on actual demand variability and the lead time. And the result is, across 23,311 SKU store combination, the value accounted for 2.37 million in excessive inventory. Applying the standard FMCG holding cost rate of 25%, which covers the storage, capital tied up, spoilage, and insurance, that translate to 593,000 euro in avoidable annual cost. That is not a projection, it's a calculation made with our own data. And it answers the question every business stakeholder should ask before funding any analytical project. What is the cost of doing nothing? Let me explain you how we build this system phase by phase. Demand IQ NL is a 7-phase pipeline. Each phase was designed to answer a specific business question, not just to process the data from one to another. So phase 1 and phase 2 establish the foundation, a star schema design and staging layer, bringing 58 million rows of raw sales price and calendar data into PostgreSQL. Phase 3 transforms that data into a clean analysis ready data warehouse. Phase 4 is exploratory analysis, where we first listened to the data and understood the demand structure, category risk, and the season pattern. And phase 5 is the forecast engine, where we benchmark two models and let the result decide. Phase 6 is the inventory risk engine, translating demand understanding into safety stock recommendations and a composite risk score. Phase 7 brings everything together in a live Power BI dashboard connected directly to the warehouse. Every phase produces something, not just output, but understanding. So folks, the data behind DemandIQ NL comes from the M5 forecasting competition on Kaggle, one of the most widely used real-world retail demand benchmark in academic research and supply chain modeling. The original dataset is US Walmart data. The first design decision was whether to use it as it is or transform it in the meaningful Dutch context, and I choose to transform. The product categories were mapped to Dutch equivalents, such as voeding, householden, hobby, and Vrijtijd. Store locations were mapped to Dutch provinces, such as Utrecht, Zuid-Holland, Noord-Holland. The calendar was aligned to Dutch public holidays, such as Koningsdag, Sinterklaas, and Kerst. This was not cosmetic. The goal was to build something Dutch hiring manager or supply chain professional could look at and immediately recognize as relevant to their business. There was also a real engineering challenge. The M5 sales files has 30,000 or more than 30,000 rows, each with nearly 2,000 day columns. PostgreSQL has hard column limit of 1600. The naive approach fails immediately. I solved this by streaming the file in chunks, melting each chunk from wide to long format in memory, and writing to PostgreSQL incrementally, turning 30,000 rows into 58.3 million tidy rows without ever loading to the full file into memory. Now, folks, phase 3 is the data warehouse, and the design choice of star schema was deliberate and not the default. The star schema places one central fact table surrounded by dimension tables. Our fact sales table holds 37.2 million rows, one row per item, store, and date, with foreign keys linking to four dimensions, such as date, product, stores, and price. The business reason is performance and maintainability. An analyst or Power BI dashboard needs to slice data by any combination of time, product, location, and price. That needs to be quickly. A flat table with 58 million rows cannot do this without significant cost. A star schema answers the same question in milliseconds. There is also a maintenance argument. When Patel Mart opens a new store, we update dim store. When a new product launch, we update the dim product. The fact table is untouchable. That separates of concern is what makes data warehouse maintainable at scale. That is why data engineers build warehouses, not because it is technically impressive, but because the business demands it. So before building any model, we spent phase 4, which simply listening to the data. The exploratory analysis produced four findings that shapes every decision that followed. The first finding was 997 class A SKUs drive 80% of total revenue. The Pareto principle holds this. Now, Pareto principle tells us where to concentrate inventory intelligence, not uniform coverage of all 3,000 SKUs, but deep focus on the ones that matters the most. Second is folding. That means our food category. That carries highest stockout risk at 15.64%. That is the number that should be on demand planner's dashboard every single morning. Third, Dutch holidays surpass demands by an average of 6.4. Koningsdag, Sinterklaas, Kerst, these are not minor fluctuations. A safety stock model that ignores them will overorder before the holiday and underorder afterwards. We embedded this into our warehouse calendar explicitly. And fourth, the Utrecht generates 21.8 million out of 27.3 million total revenue. That made it obvious starting point for the forecasting pilot. Go where money is. Now, folks, phase 5 required a model selection decision. And I want to be clear about how we made this decision. We did not pick a favorite. We ran a proper benchmark. So let's just talk about the two models here. So Prophet, developed by Meta, is widely used forecasting tool designed for business and time series. It handles trend and seasonality well and is particularly strong when demand follows regular repeating cycle. But it makes a specific structural assumption, additive seasonal decomposition, that works well on clean, predictable demand patterns. On the other hand, XGBoost is the gradient boosting algorithm. It imposes no structural assumption on the data. Instead, it learns relationship between lag demand, price, calendar features directly. It is particularly powerful at capturing nonlinear interaction that Prophet cannot model. We tested both on 10 class A SKUs from Utrecht, our highest revenue store, with identical data and the same evaluation metrics. The next slide shows what happened. So let's talk about the result. The result was ambiguous. XGBoost outperformed Prophet on all 10 SKUs. Now, not 8, not 9, but all single of them. Average RMSC improvement is 22.7% and average MAP improvement is 21.3%. On the most challenging SKUs, there is a product which is Foods 3681. Prophet produced a map of 124%. XGBoost brought that down to 42.8%. That is the difference between model that is nearly unusable and one that demand planner can trust. The reason Prophet struggle is specific. FMCG demand at SKU level is not driven by the stable season cycle. It is driven by the price, promotional, local store effects, and Dutch calendar events that do not repeat in the smooth additive patterns. So XGBoost, given the right features, learn this relationship directly from the data. The lesson I take from this, the model selection is a data question, not a preference. Set up a benchmark properly. Define the metrics before you run it. Then let the number decide. Now phase six is very important. It's a forecasting output becomes the tool a demand planner can actually use. So three components we are going to discuss. First, the safety stock. The formula is Z times sigma time the square root of lead time. Z is the service level factor. We use 1.65, which is corresponding to a 95% of service level. We accept a 5% stock out risk in exchange for not over ordering. Sigma is the standard deviation of daily demand for specific product, calculated individually per product per store. Now, this is what makes the model meaningful. The same product in Utrecht and in Groningen may have very different demand variability, and the model accounts for that. Second, the reorder point. Average daily demand multiplied by the lead time plus safety stock. This is the inventory level at which a replenishment order must be placed. Fall below this and the SKU is at risk. So the third would be composite risk score from 0 to 100. This number that combines demand variability, the ratio of actual stock to safety stock, and the proximity to reorder point. The score of 50 and above flagged high risk. That is an immediate action signal. So 371 high risk combination identify across Patel Mart's food portfolio. So what exactly inventory engine assessed? So it assessed 23,311 SKU store combination. When I say SKU, it means like a product and the store combination, and flagged more than 3,000 as a high risk, which makes actually 13.2% of entire Patel Mart portfolio. Now, further 657 unique SKUs, unique products, have some risk level. The highest risk category is the food, right, at 15.64%. These are the products where an empty shelf has the most immediate consequences. Customer does not substitute, he's not going to ask question, he's going to simply go somewhere else and buy it. Average safety stock across the portfolio is 5.47 unit per SKU store combination. Average reorder point is 17.54 unit. So in layman language, if 17.54 unit left on the shelf for the pasta, then it goes the signal that, hey, it needs to be reordered. So these are the number that is not intuition, they are calculation, individually made for each SKU based on its own demand history. What this delivers to a demand planner on Monday morning is ranked list. That, hey, here are the more than 3,000 combinations that you need to act on this week. Reorder by risk level. That level of visibility is not possible with the spreadsheet. It requires a system like this. This is the slide that answers the only question that matters in the boardroom. What is this worth? Let's talk about before and after scenario. So before DemandIQ NL, a flat 14-day safety stock rule that applied uniformly for all products. No variation for demand volatility. No accounts for lead time differences. The same logic for fast moving fooding product is for the same for slow moving hobby item. But after statistical safety stock calibrated per SKU using the Z, sigma, root, L formula, and the model knows that some SKUs need more buffer and some needs less because it has looked at actual demand distribution. The difference is 2.37 million in excess inventory and 593,000 euros in avoidable annual holding cost. I want to be clear about what that number is. It is not the estimation. It is not based on the industry benchmark. It is a calculation made with Patel Mart's own data, our SKU prices, our safety stock level, our lead time. The SQL script that produce it is in the GitHub repository. You can run it yourself and get the same number. That is the kind of business case that holds up in the room of senior stakeholders. I want to close with the three things I would take into any data or supply chain role. First, database constraints are design signals. When PostgreSQL rejected the M5 file for exceeding its column limit, the right response was not to find a workaround. It was to redesign the data model. The result was a better architecture. A production system are not defined by when the things work. They are defined by what happens when the naive approach fails. The second thing that I want to keep in my mind that model selection is data question. Prophet is a good model. XGBoost is the again good model. Which one is right depends entirely on the data. Running a proper benchmark and being willing to accept the result regardless of which model you assume would win. And that makes separate of analytical thinking from the preference. Third would be the business value must be calculated and not assumed, at least forecasted with the high confidence level. The inventory engine was accurate. The risk score were meaningful, but without 593,000 euros figure, none of it reaches to the senior stakeholder. Technical correctness and business relevance are two different things. You need both, and you need to be person who builds the bridge between them. The full project is on GitHub. The live dashboard is also link provided. Thank you for listening and